Welcome to SMR X Hackathon Design Challenge Lecture Series. My name is Sharman Perera. Today we have Dr. Kirk Atkinson talking about Small Modular Reactor.
Good afternoon, everybody. As Sharman just said, my name is Kirk Atkinson, and I'm the director of Ontario Tech's Centre for Small Modular Reactors. It's a new centre. I'm going to talk to you about small modular reactors today, entitled Designs, Opportunities and Challenges, and I'll get straight ahead. So, quick disclaimer while I'm here. I prepared this lecture for the hackathon itself. The general idea being is I give you some ideas about how SMRs work, the kind of things that I thought about. In so doing, I've used some examples from various different vendors using their information. And there are vendors that I haven't used. To suggest that the other vendors are no good is not true. So I absolve myself of all responsibility in that. Thank you. So first off, let's think about where we are now with nuclear reactors. Most of you will know that in Canada, we have a good history of using nuclear power. And we have a number of large stations. As you see one there, you see Pickering nuclear generating station, not far from where Ontario Tech is. This is going to be shutting down in about 5 years' time or so. And there's going to be a bit of a gap in electricity generation. Now, that could be picked up by other means. And you'll have heard the other day from Jennifer McKellar about different kinds of renewable technologies. And we are doing major refits on our nuclear plants elsewhere in Ontario. So there is a range of other possibilities, but is that gap going to be fully filled? And is it going to be filled in a environmentally friendly way? So this is where we'd like to be, the next wave of nuclear innovation. So small modular reactors in Gucci-looking buildings, remotely dispersed or in points where power is needed, as opposed to large stations that exist on the edge of lakes, etc. So, brings me into the point about designs. So, how do we make electricity? Well, fundamentally, we've got a heat source that boils something, is the typical way, to make some kind of steam, to turn some kind of turbine, which will turn the generator and make the electricity. Doesn't really matter what that heat source is, it works in pretty much the same way. A reactor is just another heat source. So you'd have spoken or you'd have seen Filippo Genco speak a couple of lectures ago, and he would have given you an introduction to nuclear power, to nuclear science in general. So I need to recap that very briefly. So we've got different kinds of reactor. They work on the process of nuclear fission. So a neutron gets absorbed in a uranium nucleus, typically, can be plutonium, can be other things too. It excites that nucleus, which splits into 2 bits, typically, and gives off some gamma rays and some neutrons in the process. Now, if we just had nuclear fuel and say it was just in air, those neutrons will bounce around. They might create some fission events in fuel, but they might not. Fast neutrons, when they collide with uranium or plutonium nuclei, which we call the fuel, will kick out typically 2 to 3 fast neutrons. But the probability of them being captured in the first place, even though they make 2 or 3 neutrons, is quite low, because fast neutrons are hard to capture. They travel quite far. They leave small spaces quite readily. Now, a fast reactor basically consists of fuel, and something that it doesn't contain is a moderator. Thermal reactors, on the other hand, we introduce a different kind of material. Could be water, could be plastic, could be graphite, could be a bunch of different things. The idea of that material, which we call a moderator, is that it bounces the fast neutrons around a little bit. Every time they bounce around, they lose a bit of energy. And when they're slow moving enough, they're more easily captured. Now, that limits the choice of fuel that we can use, typically to uranium-235, which is the normal stuff that we use, or plutonium-239. Materials that you've probably heard about in films, and you can read about it, a bunch of different things. When either of these two nuclei fissions, we get off typically 2 neutrons. So it gets you slightly less neutrons than a fast fission would. But the chance of the reactions happening is bigger. Not the only thing that can happen. We can still have some fast fissions in a thermal reactor. We just get less of them relative to the amount of slow fissions that we get, slow neutron fissions. We get leakage of both fast and slow neutrons, and a bit like the way you lose heat. So if you've got a big surface area, things dry quicker than if they got a small surface area. Neutrons are lost in much the same way. If your reactor core is small, you're going to have a lot of leakage, which means you might want to think about ways that neutrons can get bounced back into your reactor. And there's always stuff that's in your reactor that can also absorb neutrons. And it, like for thermal fission, it prefers slow neutrons. In all cases with a reactor, we need to take the heat away. That heat's pretty important. The heat comes predominantly from the kinetic energy that is transferred to the fission fragments. They're the 2 nuclei or 3 nuclei that your uranium nucleus, 2 nuclei that your uranium nucleus will split into, and it carries off the kinetic energy. Now, when it does this and it moves through matter, it works a little bit like friction and creates some heat. And that heat will be in the fuel. And there needs to be a way to remove that heat. And there are a bunch of different ways you can do that. Heat will be lost through radiation, but it's a small amount. So typical ways would be conduction, convection, or a mixture of the two. Now, typically, you're going to have conduction from the fuel out to some kind of fluid that will move and take heat with it. Now, if we don't have cooling, the fuel will melt, perhaps. Doesn't always melt, depends on the kind of fuel that you choose. Depends on how much heat you make. So if you pick particular kinds of fuel, they'll be more at risk of melting if they get hot than others. And if there's not so much heat being produced overall, then the chances of melting going beyond the melting point is going to be low. So all reactors need that. Now, another thing that happens with temperature, with that heat, is that properties change. Yeah. Now, typical properties that change is density. So if we cool our reactor with water or heavy water, we all know that water will change in density with temperature. There's some funny things with changing in density of temperature as well, because we know that if it freezes, it expands. That's pretty unusual. But when you heat up water from, say, 4 degrees Celsius, and you keep heating it and heating it and heating it, eventually it becomes a vapor. We know that. As it warms up, that less dense water will take up more space. Therefore, there's a bigger distance between adjacent nuclei to scatter off of. That's one aspect. And that happens in other materials too. Material will expand. To a point, structural materials will expand as well, and as does nuclear fuel and other moderators too. So in effect, it's changing our number density within a given volume. Now, on top of that, we have something called cross-section, which is basically chance. We all know if we toss a coin, it will either land heads or tails. Now, we know that if the coin is perfectly balanced and everything works perfectly well, there's a 50% chance that one or the other side will fall. Now, chances of reactions, nuclear reactions, are also probabilities. They're a lot more complicated, but you can express it in terms of a number. And it really is a number that expresses how big the chance is. And we call it cross-section. as energy of our neutrons goes up, or temperature of our material goes up relative to it, cross sections typically decrease. Yeah. Now that's not always the case. There is some other effects that happen specifically in fuel, but quite often as the temperature rises, the cross section will change for certain reactions. Now, equally, when things heat up, there's also vibration. Vibrational energy that's from the heat will make molecules and atoms move a bit faster. And that also has an influence on the cross-section. And all of these things change reaction rates. And reaction rates of capture of neutrons in fuel will dictate how many fission reactions we get. And that will dictate what the power is in our system. So if we can change the cross-section somehow, or we can change number density somehow for other reactions, predominantly the reactions that slow down or keep neutrons in, we will change the amount of chain reactions we can have. Now, brings us to the CANDU reactor. So the CANDU reactor, I'm sure that Filippo spoke about this, is Canada's great nuclear achievement. Very successful reactor design that's been sold overseas. Has some particular characteristics. It uses heavy water as its moderator. It uses natural uranium fuel, so unenriched fuel, which is very good for Canada because we've got a big supply of natural uranium fuel. It loads its fuel assemblies horizontally, and it has a heavy water coolant. That's quite important because if it wasn't heavy water, we'd snap some neutrons from the system, and it wouldn't be a very efficient system. Now, that transfers its heat to a steam generator, which makes steam, which turns our turbine, which I've already said about. So, three fundamental things in that system that we want to consider. The coolant, so i.e. what's cooling the fuel down, the fuel itself, which in the case of the CANDU is natural uranium, and the moderator. So whatever the moderator material is. In the case of the CANDU, it's heavy water. Now, let's think about the positives and negatives of large reactors, such as CANDUs. The positives are we've got large power outputs. We make a lot of power. And we make a lot of power in one place. The technology is proven, been used for decades now. So we know how it works. We've got companies that can make the components. And if any of you look at the amount of CO2 generated in Ontario every day in electricity generation, you'll find that we're extremely competitive. In fact, one of the best jurisdictions in the world because of the fact that we use so much nuclear. Some downsides though of large power reactors. They're big in a number of different ways. Their site might be big on where it's based. That might be for reasons of security, might be for reasons of safety, might just be because they need more space. The big containment buildings, we see them from a long way off. Takes a lot of material to make those buildings. They're built to order, if you like, on site. The components inside are big. There's many components typically. Also, they're expensive. A couple of companies worldwide have gone out of business in the last few years when they've tried to build large reactors. In the UK, where I'm originally from, the current build of a large power reactor is running at over $30 billion. $30 billion to make it. Now, provide all the electricity, but it's a huge investment. And we all know that when something goes wrong, a large reactor has a big impact. Now, that could be as simple as a trip. So the reactor trips for some reason, and it stops generating power. Well, if you're reliant on a huge amount of power from that reactor, that could have a significant impact on your home life, your economy. Equally, if there is a failure of some sort that could give rise to an accident, we know that there's been a few incidences in recent years and before where major nuclear accidents have occurred. Don't happen very often, nowhere near often if you consider the amount of reactor hours that are successfully used, but they get into the media, they get into people's consciousness. So they're things to think about. So what we really want to do is think about how we can keep all the positives, the output, the technology that we know, zero carbon, and lose all the negatives, or rather, change large to small, expensive to cheap, and big to little. And that brings us to small modular reactors. In this graphic, we see a large reactor, which is a 4-loop pressurized water reactor, typical of what you might see from Westinghouse in the US. And then to the left of it, you see a range of different small reactors. Now, some of them are more mature designs than the others. But if you look right down in the bottom left, you can see a Volkswagen Beetle. So typical small car, popular in the 70s especially, and before I had one. I'm not that old. And you can see as a scaling factor that you can get reactors that are not much bigger than a few cars high and not as wide. They can be very small. The question is, what power output do they have? Yeah, and they can be quite big, for that small size. The little one that is next to is showing you this going to make 25 megawatts electrical. Yeah, that's a lot. When you think about it, that's enough to power, a small town for sure. So maybe 10, 20,000 people, maybe a local industry, a bunch of different things it could do. So you can make a lot of energy, make a lot of power from something that's comparatively small. So brings us to problems now, which we see as we go forward into the SMR world. Fear of failure or just fear. We know that people are afraid of radiation. They're afraid of nuclear. World War II, the Manhattan Project produced the atomic bombs, and everyone's seen the picture of the mushroom cloud. People associate nuclear power with nuclear weapons, which it is not. Your nuclear reactor down the road is not going to act like a nuclear bomb. It won't happen. But that doesn't mean that accidents can't happen. And we know that in 2011, a unusually big earthquake produced a tsunami in Japan, which caused the loss of the Fukushima Daiichi nuclear generating station. And we probably all seen pictures of that and explosions of the hydrogen gases, etc., that's coming up. Now, we can look at 1986, going back a bit further, and in the Ukraine, there was a big accident that has been turned into a TV show, I think it was HBO, called Chernobyl. Overly dramatized on the TV for sure, but definitely big, major impact. Spread radiation across a lot of Northern Europe. Meant kids in schools had to have potassium iodate tablets. Now, both those two events had very clear reasons why they happened. Fukushima's case was the predicted worst case scenario earthquake and tsunami was ignored. They knew that under a worst case scenario, the flood defense walls would be overcome, and they were. Just because it said it's a 1 in 1,000 year event doesn't mean it won't happen in the first year of that 1,000 years. It's probability. And it washed out a lot of the safety systems that would have prevented bigger impact of the accident. In the case of Chernobyl, we had a more risky design coupled with malpractice, if you like. Neither of these two things should have happened. We would never be worrying about nuclear power if it weren't for these kind of things. 3 Mile Island happened in '79, so there was an issue there, but not much impact of that. But because we see these things, it means that nuclear power is held to a higher standard. So any new kind of nuclear power generation needs to demonstrate that it is much safer than the past. So how do we reduce that risk of failure? Well, we can rely on passive safety, rather than engineered safety, or engineered safety over procedural administrative safety. If we work from the bottom up, we think about procedural administrative safety. Most people in the Western world right now are under some degree of lockdown. Some people are following the rules, some people are not. Some people are going outside more often than they should, are visiting the store more often than they should, are not social distancing. Now, the consequences of that to individuals could be significant, but the consequences to the wider population might be less. In a nuclear plant, if somebody was to break the rules, as has happened, then the impact can be large. So that brings up engineered safety. We build systems that make us safe. So one of the ways that happens in a reactor is the ability to scram the reactor. And that's what happens when they drop control rods into the reactor upon a trip of some sort. And that trip might be they exceed a certain threshold of power, or they exceed a speed of how quickly power increases. So we have a safeguard that shuts the reactor down. We have cooling pumps that take heat away. All of these things can exist and do exist. But systems go wrong, pumps fail, control rods can get stuck. So you have to build in extra allowance for those things going wrong. Brings us to passive safety. If you think about passive safety, what passive safety is relying on things like gravity. Gravity is not going to switch off, at least not in this universe. Vapor rises. When it hits a cold surface, it condenses. We can rely on those facts of nature when we build our reactor. One of the biggest risks is decay heat. When reactors shut down, the radioactive fission products that are in there continue to decay and they give off heat. And when we shut down, that's something like 7 to 8% of what it was before it shut down. Now, if you're running at, say, 10 megawatts, that means 700 kilowatts of heat. That's a lot of heat. We consider a kettle might be 1 kilowatt or 2 kilowatts. Thankfully, the fission products decay away quite quickly, the short-lived ones. They produce most of the heat because they're decaying quickly. So they're giving out energy quickly. So we can lose that in a matter of a few days. Long-lived fission products hang around a lot longer, and we know that's part of what the legacy nuclear waste is. In all cases, though, it's important that we have a decay heat removal system or method to prevent the core from melting down if the cooling systems themselves were to fail. And it brings us to the concept of what we call walk-away safe. This is like the holy grail of reactor design. That something goes wrong, you just walk away and leave the reactor and it'll be fine. And traditionally, there's been few reactors where this can be the case. And those that have existed are typically experimental or research reactors that make much power. But we can see how the decay power changes over time. We can see that we initially had a large amount of power at 1 second, which then drops off to much less after an hour, which down to 1/10 of what it was before after a day. After 3 days, we're down, until sometime later, we're effectively making little heat. Now, the important thing there is that we need to have heat removal mechanisms in place for each one of those areas. That's one of the major aspects of SMR. So right now in Canada, there are around about a dozen different SMRs that are under consideration by the regulator, the CNSC. They have a range of different concepts and a range of different companies. Terrestrial Energy is a Canadian company. Ultrasafe is building at Chalk River. Med Cold is from Sweden. Arc Nuclear is a Canadian-American venture. Moltex is a UK-Canada venture. Moltex is American. NuScale is American. U Battery Canada is UK-Canada. GE Hitachi, X Energy, Westinghouse. Tons of them. And you'll see there's a lot of different model names there, and a lot of different types. We've got molten salt reactors, high temperature gas reactors, liquid metal fast reactors, sodium fast reactors. We've got pressurized water reactors, boiling water reactors, micro reactors. We've got a bunch of different things. Now, when we look at them, we can see what kind of electrical output they can make. Some are much bigger than others. Yeah. And we can see that they differ in what kind of coolant and moderator they have. Yeah. Some have fluoride salts, some have uranium tetrafluoride salts, some are helium cooled, some are water cooled, some use UO2, some use highly enriched fuel, some use triso fuel, some use HALO, which is a high assay, low enriched uranium. So basically just short of 20% uranium, 235. If we box these up, we've got 3 concepts that are basically water reactors. We've got 2 that are fast reactors, various types. We've got a couple of salt ones. We've got some high temperature gas reactors. And we've got a little one that is that uses heat pipes, which is interesting. Now, if you think about reactors worldwide and experience of those light water reactors, PWRs, BWRs, there's a lot of experience around the world in them. They're the most commonest type. Pressurized heavy water reactors are popular in Canada and a few other countries. Light water cooled graphite moderator reactors, not so many of them anymore, and they're possibly unsafe. You know, Chernobyl's reactor was one of these types. Gas cooled reactors, lots of experience in the UK, didn't really make it outside of there. And fast breeder reactors, not much experience there either. So we can see where the experience is in existing technologies, and we can predict which ones of those ones from our list before are more likely to be available soon. So I'm going to touch on a few of those different SMR concepts and describe some of their features and their levels of maturity. So first off, we can look at NuScale's power module. It's the closest to market SMR design. It's a PWR. PWRs have been around for a long time. You know, been around since the late 50s, early 60s of last century. I can say century now. Been used on nuclear submarines for a long time. Used in France for their electrical generation. Many places have these. So PWR technology is really well understood. And consequently, NuScale has been able to make it closer to market than the other vendors have so far. And that might mean that they win the battle, win the race for SMRs. So we can think about what it's got, you know, and there's a graphic on the left, and it shows you that at the bottom of this big long tall cylinder, effectively, is a nuclear reactor core, a bit like I showed at the beginning. Then as we move up, we have a riser, and above that we have steam generators. Now those steam generators, they are where we transfer the heat. So we flow water through the core, take the heat away, take it to the steam generator to make the steam. But we see that the steam generators in NuScale design are within the pressure vessel, which if you saw the picture that I showed you of the large PWR earlier, the steam generators were outside of that containment. So this is one of their features, is that they bring it into the same vessel. This is why it's an integral PWR. There are steam lines and feed waters and various different other factors there. It relies on typically natural circulation of reactor coolant. And consequently, that reduces the need for obviously pumps. Now, in so doing, if you design your reactor right, that flow of water around your reactor means that even if you walk away, as long as there's the water there, it will continue to flow. It will go through the core, it will get heated, it will expand, and it will rise. As it rises, it takes the heat away from where the fuel is. And then as it cools, it will fall back down to the bottom. And you can continue to do this as long as there's not a leak. Now, one of the ways to get around the leak is by having the steam generators inside of the vessel. Some other factors that it's got a higher strength steel containment, 10 times higher pressure rating than typical PWRs. It's got volume of water to its power that is 4 times better than others. So here's a much bigger reservoir of cooling water. And it's only got 5% of the fuel of a large reactor, which brings us to that impact point I said at the beginning. So if an accident was to happen, the amount of radioactive waste, the fission products that could be released to the environment, is going to be 20 times less than it would be from a big plant. So much smaller impact. Yeah. Now, when we see how these things are designed and they're installed, we can see that they are in a bank of modules. There's a crane that can load new modules in. They all sit under a biological shield or water shield that provides extra cooling around the outside as well as shielding from neutrons. It's available to be refueled, and there's a refueling cycle for it. And you can see that they're kept in a steel-lined concrete pool, under the ground. That has a number of advantages. It means it's less susceptible to attack from above, say by an airplane. It also provides a shielding enhancement. And the concrete pool is lined with steel, therefore making it more resilient. Now, we saw hydrogen release that can happen from light water reactors, such as we saw Fukushima. And the containment vessel will keep that hydrogen inside of it. And as there's no oxygen there, it means that combustion can't happen. So the big explosions that you might see can't occur. If you think about the passive long-term cooling, it's the same graphic as we saw before, but we can see that as the water boils off, the pool outside takes that heat away and it evaporates. As it evaporates, the volume of water that is there is still sufficient that enough of the heat has been taken away before all the water's evaporated away. So eventually, air cooling alone is sufficient. And NuScale's design, they can have up to 12 units on the one site. So although an individual unit might only make, say, 60 megawatts of electricity, if you put a dozen of them on site, you're then up to 720 or so megawatts. So you can be a drop-in replacement for a larger nuclear plant. And one set of control people can monitor all of the reactors. So lots of automation has happened. So they can automate the design. They don't need to be there. They don't need multiple operators for every reactor. That's what we see there. So it's barriers to fission product release. We can see on this graphic here. Conventional designs have the fuel pellet and the cladding. So basically, you can think of cladding as like a tin can around something within the tin can. The fuel is the stuff that's in the can. And there's a vessel within which the system is, the core is contained, and then there's containment outside. And in case the vessel is breached, we'll contain everything within it. So NuScale's bunged in extra water, extra lining, extra shielding, as well as a different building. And if you want to compare against Fukushima, Fukushima required diesel generators to carry on providing fuel. NuScale does not. Fukushima required external water. NuScale does not. Coolant pumps were were necessary for Fukushima. They're not required in NuScale's case. Needs a spent water cooling for the spent fuel. Less of a problem in NuScale. All of these factors make NuScale more resilient than Fukushima. And it is the most advanced design, the most progressed design. It's the closest to market design. So you'll have seen I've talked a lot about that. When it comes to something like ARC, which is a reactor design that is being built or being proposed to be built in New Brunswick, this is based on an integrated sodium-cooled fast reactor design. So they use a different kind of fuel. They use highly enriched metal fuel. Only needs refueling once every 20 years, which is different to what NuScale needs. And it can burn nuclear waste, which is good. It operates under atmospheric pressure, which is a big deal, because when you've got a PWR, like NuScale is, you still have pressure there. And that pressure is because water will become steam if it's not kept under sufficient pressure. And that means you need a pressure vessel to contain the reactor, which is hard to make to the right standard. Yeah. The arc reactor is different, as you see, because it doesn't have that. So if you think about the human scale, you can see the little person sort of on the little lead of the little platform above the reactor, and you can see at the bottom of it, the core's at the bottom again. And there's a pump, and this pump helps circulate the cooling sodium, and it's sodium, liquid sodium. Yeah? And sodium, if you get water near it, it's not good, but it's kept within its containment, and because it's a metal, it has a very high thermal capacity, and it's got a low melting point as metals go, and therefore it takes off a lot of the heat. It has no moderating capability, so this is a fast reactor. So there's no neutrons slowing down. The neutrons remain fast, and that coolant, that sodium, doesn't do anything much with those neutrons. It's effectively neutron transparent. And then you see that there's a heat exchanger that takes heat out of the tank and drives the system. This is based on a technology called PRISM that was from General Electric Hitachi, and you can see the graphic there. And you can see how that it involves multiple loops and a steam generator turbine to make power, like that one. Now, there's a lot of experience in that. Argonne National Lab in the US operated the EBR-2 reactor from 1961 through to 1994. So the technology is fairly well advanced and understood. It's got a passive heat decay removal system, like we see, not relying on pumps for it. The heat exchangers are in the tank. And because it's not got because the coolant is not passing through these pipes, it sits in a vessel, its chances of LOCA are removed. So LOCA is a loss of coolant accident. You see how it's installed. You see it's installed again in the ground, taking advantage of the extra shielding and the physical security from attack. Obviously, the electrical generating side is on the surface. Now, you'll see that I've only done a few slides there. That's because ARC, their design is a lower level of readiness to NuScale. That doesn't mean it's going to be less good or better than NuScale. It's just that's where it is right now. Another technology being developed out in New Brunswick is the stable salt reactor, which is a co-venture between the UK and Canada. You can see a kind of schematic core there, where it shows some passive cooling ducts that are able to cool the vessel, take the heat away. It's got a heat exchanger pump that is able to take heat out of the coolant salt and send it to a further heat exchanger to make steam to turn thermites. One of the advantages about this design is because it has those vents, those ducts for air cooling. If the heat exchanger was to fail, and the pump was to fail, then cooling can be maintained. So again, we have now passive cooling. We're relying on airflow. Unless you decide to put this thing in a vacuum where there's no air, so considering that your issue is space, that could be a problem. Then this is good to go on Earth. And this thing is able to be refueled online. So we see another picture of it there. You see effectively it sits in a tank. And again, a bit like the arc reactor, it doesn't require very high pressures. Now the coolant, there's a whole bunch of characteristics about the coolants and the fuel mixture that you can look at. But you can see that there is three loops in this system. So there is the initial primary loop where the cooling salt is. There's a secondary loop that takes the heat out of it, and there's no direct physical contact between the two salts in the two vessels. And there's a third loop where it changes it out to make usable power of some sort. Now, one of the big differences in their design is because they use a salt, they actually keep a salt in a pin-like structure rather than flow salt around. That means that they get rid of a lot of the problems with respect to chemical corrosion, and they have a vent on the top of their fuel assembly that allows fission product gases to come out. That prevents some of the expansion problems that other reactors would have. And it means you can model these things more easily. Here is a section here, and once again, you see that it is sitting underneath the ground. There is an airlock for the module changes, and you can see how the fuel assemblies fit into the core module design. Now, one of the things that with this design is that it is a rectangular configuration, and it can be fueled whilst online, which is unusual for reactors. CANDU reactors do this right now. But a lot of reactors don't, because normally you have to open the containment. So this is an advantageous way of doing things. Reactivity control is through temperature coefficients and fuel loads. So temperature coefficient was like I was saying earlier. As things heat up, reaction rates will change, so we can reduce the amount of power. And it's got some boron ones to shut down. Where are its advantages? It's much smaller than a conventional reactor. Shutdown will happen as it gets hot. So it will shut down automatically as it warms up. Continuously bees refueled, so it doesn't need to shut down. It doesn't have start of life reactivity excess. Modular can be built in the factory. Steam turbines are normal standard ones, so they're built off the shelf. Continuous air cooling means you don't need a backup system. And again, the below ground gives a good advantage for safety. Now, that was a molten salt system. U-battery is another UK-Canada co-venture for a much smaller kind of reactor. Whereas we might be able to make hundreds of megawatts for some of the other designs, U-battery's design is for a different market. It's to provide power to remote communities. And typically would provide something like 4 megawatts of electricity or 750 degrees Celsius process heat. It is a high-temperature gas-cooled reactor that uses helium gas as the primary coolant, which cools the fuel, and then uses nitrogen, so the heat is transferred from primary to secondary side in a gas-to-gas heat exchanger to nitrogen. And obviously, nitrogen is in the air. Can be installed above or below ground, and uses a kind of fuel called trizo fuel, which you can see on the right. Now, trizo fuel is a bit like an M&M in that you have layers within your fuel pellet. So the kernel itself, or fuel, the uranium, sits in the middle, and then there's some graphite that sits around it. Then there's a silicon carbide layer, which is very resistant to temperature and breakage, and then there's a high density graphite that goes around the outside. And these little pellets are all put into what they call a compact. So they're effectively pressed into a graphite cylinder. And that graphite cylinder slides into a graphite block where there are coolant channels for the gas to pass. And a number of these different graphite blocks will form the reactor core. And this is how their design work. So it's got a lot of similarities with the advanced gas reactors in the UK, but it still requires gas. You can see how it's installed. You can see the different parts of the system: a turbine generator, heat exchanger at 0.2, reactors at 0.3, a maintenance deck, a used fuel store, and various other bits and pieces going on. Now, this will also shut itself down with increasing temperature because the graphite will moderate less well. And so that's highly good. It's got a high cycle efficiency for producing the actual output for the turbine, 40% or so. And triisofuel is very resistant to temperature. So even if the system heats up really hot, it won't melt. So meltdown won't happen. So there's lots of inherent safety aspects with this that exist. And we have the ability, or it has the ability, that natural circulation of gas around the system will provide additional cooling through. Brings us to the final design I wanted to talk about, which is eVinci's Micro Reactor, and they target a different kind of market. They're a very small reactor. They're not aspirations to become big, and they use a monolithic kind of core, which you can see there, that sits within a stainless steel vessel, and the core sits within the middle, but it uses heat pipes, and that's a very interesting point because it's effectively relying on a conduction mechanism, albeit that the heat pipes have a fluid within them, sealed within them in this case. But in effect, you may as well think of it like a copper bar that is taking heat out of the reactor core, and that's good because it means you don't need the same kind of coolant materials to cool the core down. So that's what we see with this design. Again, less available in this, but one of the aspects about it is that the core is very small, and therefore is very susceptible to leakage. So it relies on a reflector around the outside, which you see in this position here, the kind of grey area, to reflect neutrons back into the core to make it more efficient. Else we would have too much losses. So this effectively is going to be then a thermal reactor because of this, because we're slowing down the neutrons and bouncing them back in. Now, in all of these designs, there are positives and there are negatives again. So the negatives we saw before were large, expensive to build, and big individual impact. But we now see small modular reactors allow us to get large power outputs, but it might need multiple units to be brought together to be able to do that. It still provides zero CO2 emissions, or near zero CO2 emissions, if we exclude the build processes. Technologies may or may not be proven. You know, some of them are quite advanced. I've talked about the PWR technology being well understood, and the arc kind of reactor technology being quite good and quite understood. But some of the others maybe need a bit of work. They're small by definition. They're cheap to build in principle. So their cost becomes less as more units are built. So the first of a kind is going to be expensive, but once you go beyond first of a kind, price comes down. And like I was saying before, because they have much less fuel within them, if something goes wrong, the per unit impact is much less. So the impact of the environment is much reduced. So it brings us to the idea of opportunities. So where can SMRs be used? So here's a map of Canada. This is from the Canadian Small Modular Reactor Roadmap, which was put together in late 2018. We can see places where small reactors might be useful. Well, we know that there are 17 coal-fired power stations. Yeah? They produce a lot of CO2. We can replace them because small modular reactors kind of fit the size, the power output capabilities of these reactors. So they could be a drop-in replacement for these kind of reactors without needing the same footprint that a Pickering type station would need. We can think about remote communities. So we know that Canada's got a lot of remote and indigenous communities where the price of orange juice can be, 27 bucks, per litre, just because the cost of energy to get it there and everything else is so expensive. Yeah, we know it's expensive right there. It then creates a problem. They use typically diesel to provide power in these remote places, which is expensive to get, polluting. We don't like that. And their lack of power, impacts the quality of life. So a drop-in SMR, small one, such as a U battery or an eVinci, might fit their requirement. Equally, it could provide the power for mines. so that we can do these extractive industries that Canada's economy gets great benefit from. We know about the oil sands production, very energy intensive. Maybe energy production or oils will be produced more cheaply if we used SMRs in the future. Right now, obviously, it's not looking so good, but that could change. And then heavy industry, if we need steam, hydrogen production for buses, it needs a lot of energy to make that hydrogen. And some of these high temperature reactors could provide that need, fill that need. If we look at the little map of the world, we can see where there's potential market. Those purple blobs show you where there's potential markets. There's some generating capabilities required. So we can see where that there is a lot of places where this could be done. Now, other advantages about SMRs. Here from Moltex, they propose an idea of working in tandem with renewables. Just because I'm talking about small modular reactors doesn't mean that I'm against renewable energy. I think they both play a part. What we need to get rid of is fossil fuels. No. But we do know that when it's nighttime, the sun isn't shining on us. We know that if the wind doesn't blow, the turbines don't turn. We know that if you've got certain kinds of tidal power systems, if you had ice, it could cause you a problem. So all of these different things can be an issue for Canada. So what you can do is you can use your SMR to provide the power when the renewables aren't able to provide power, or to charge storage. In this case, they're using hot salt, but it could be batteries as well, or different kind of energy storage, to put that energy in so that it can be recovered later. Can be used to burn some of the CANDU fuel that exists in Canada right now. We know that there is a lot of legacy nuclear waste in Canada from our CANDU stations. Moltex's SSR and Arc 100 design both potentially can burn used fuel and therefore reduce the fuel burden that we have to dispose of in the future. Could also be used to take to remote places. So here we see Westinghouse's eVinci design, which is a version of the eVinci that they just got a contract from the US government for military purpose. It could go on the back of a truck, so you could fly it to a war zone. But equally, if you don't like war, which none of us should really like, it can go to disaster relief or remote places where there's an emergency. You could fly in or truck in the reactor to provide power. We think about hurricanes in the Caribbean, and we can think that they lose all ability to make power there. So this could provide a solution for that, disaster relief. And we know that fossil fuels are very bad, and we know that in terms of footprint, so energy density, the amount of energy made per unit volume, nuclear reactors will always win out over renewables. Renewables have things that are against them. Renewables, as we make more of them, it has an impact on the materials we need, which can have a consequence we haven't really established properly yet. And if you think about what's happening in terms of the different provinces in Canada, back in December of last year, the three premiers from Ontario, New Brunswick, and Saskatchewan signed a memorandum of understanding to cooperate on SMR development and deployment. They're seeing advantages, and more recently, Alberta has expressed an interest in being involved. So we can see that SMRs potentially have a future in Canada, and there is government support. But what are the challenges? First off, money. Like anything, SMRs is a business. SMR designs are not being designed by the government. They are being designed by companies. Some government funding, but ultimately companies. And companies will only be able to, will only build SMRs if the business case can be made. The business case is key. So you need to show that it's economical over its full lifetime. And that's an important point, over its full lifetime. Because building one today might be expensive, but if it lasts 20 years, then that's then it could pay for itself. But like if you think about your car and you go down the gas station and fill it up, how frequently do you fill up the tank? If you drive a lot, quite often. So, whilst the tank filling up might not be too much money, when you do it a lot of times, it can add up. Other things, materials and manufacturing. So many of the proposed SMR designs that I've talked about and the others are using new materials or new manufacturing techniques. Some of them need more qualification than V&V. On the left there, you see a picture of the 3D printer that has printed the components on the right. Yeah. Now we're at the point where we can actually 3D print reactors. Can you imagine that? This is not requiring specific forgings. You can actually use a 3D printer and you can do this. But are those materials resilient enough? Do they have the same characteristics? Some of that needs doing in some of those designs before we can actually get them licensed. Fuel. All of the SMR designs use some level of enriched fuel. Canada uses natural uranium fuel in CANDU reactors, never done enrichment. Doesn't have the capacity to do it, so we need to address that in Canada. How do we get our enriched fuel? Do we need a process to do it at home? Also, let's talk about the waste. So right now we lack a permanent storage for nuclear waste. So the idea of making more is going to be a hard sell to the public. And that brings us to the point of social license. Whilst I can sit here and I can talk to you about the benefits of reactors in general and small modular reactors specifically, a lot of people don't like reactors. Right? A few months back, we had the emergency alert from Pickering, but it wasn't actually from Pickering. But the amount of concern that caused was large. So there are a lot of people that won't look at the science. They will just look at the nuclear power is bad argument and imagine that it's an atomic bomb. It's going to kill you. And they don't see the advantages in terms of reducing CO2 emissions and therefore saving the planet. Other problems are deployment. How do you get it there? Well, unlike a large reactor, you might be able to get it on the back of a truck or a rail car. You might even, for a very small micro modular reactor, you might be able to fly it on a Chinook helicopter or something like that, or a C-130 airplane to deploy. So we've got to think about that. But it also constrains where you might want to put it, because if you're going to put it in the north, how are you going to get it there? Do you need to go on an ice road? Is the ice road going to be strong enough for the weight, for the load? So you can see that there are troubles in where you're putting these kind of things. So that's one of the key things that work needs to be done. Which brings us to your problem, SMRs in space. Space, the final frontier. My name is Kirk, obviously. You can think about what troubles you might get. How are you going to get it there? How much power do you need? What are you going to use as your materials? Do you need to put it, subsurface, or are you going to take an excavator to Mars to dig out the space, or do you want to drop it on the side? Do you need residual cooling water, like a big tank filled? Where are we going to get that water from? All of these things you need to think about. So how will you make it? How will you get it there? What local facilities or materials do you need? In other words, pretty much exactly the same things that you need to think about deploying SMRs anywhere else, including in Canada. So space is just another deployment location that we need to think our way through. I say react on. And that's me done. Any questions?
Well, thank you, Kirk. It was a very resourceful presentation. I have a question just to help students. So as you mentioned that the one of the criterions for this SMR X Hackathon Design Challenge on June 6th is to basically take this material up to Mars. So also they need to think about some other sources of power in it in case if they need extra. So can you actually see the way that you can combine the SMR with any other renewable technology such as solar panels, like when they want to deploy that to colonize the first human population on Mars?
Well, when you think about somewhere like Mars, there's obviously a few things to think about. First off, if you're going to use solar power, for any form of energy generation. Are you getting enough light from the sun to do it? Where is the surface of or your location on Mars relative to where the sun is? You could arguably couple those two things together and have some kind of reservoir of salt, a bit like what Moltex have proposed. Their design's quite elegant in that they're using energy storage. They use the reactor to make heat that they can able to put into the salt reservoir. So that those two things could go in tandem. I don't know about the geological basis of Mars too much in terms of whether you can get any heat from inside of the planet itself. Obviously, it has a very different environment in terms of gases, but it does have a gas atmosphere. Yeah, there's a number of different considerations to think about in terms of that. But yeah, for sure, the ability to use it in tandem with other energy sources, and maybe, but you could ask yourself, if you have a suitably large reservoir of energy from a nuclear reactor, why bother with the less efficient solar power? Yeah. At the end of the day, you're taking your power source there for a reason. You're going to need to be making your sufficient oxygen for yourselves, because obviously it's got a CO2 kind of atmosphere. So you think about those kind of things. Could the atmosphere there be used as a coolant? Perhaps it could. So I don't know. So these are the things you need to look up and consider. If we're thinking about the capacity as coolants, back in the UK where I'm from, the advanced gas reactors, they use CO2 as their cooling gas. So we know that there's lots of CO2 on Mars. So we don't know so much about how much water there is. I believe there's some, but this is not Total Recall, the original film.
Okay, so this will bring us to a few more questions, just the follow-up questions. As you mentioned earlier, one of the restrictions that you have is which reactor to take to the planet Mars because of the payload restrictions. So they need to have a vehicle that can take this reactor up to Mars along with the rest of the people who are going to go on board. So based on the reactor design that you have presented, do you have a preferred one that would basically have a lighter the mass compared to anything else?
Well, there's two ways of thinking about this, aren't there? You can consider whether you take it as one unit or you can take it in components. Taking reactors into space is not a new thing. It's been done already. The Russians, for sure, they had nuclear-powered satellites in the past. So you can think about these kinds of options. I would argue that first off, you need to figure out what power you need, how much power you need. Because when you're thinking about it, 20 megawatts can run a lot of stuff. The aircraft carriers that I sometimes see back in the UK, they have something like 10 megawatts, of power that they produce, something in that kind of zone. So that's for 1,000+ people and lots of services and moving a ship around, which takes a lot of power. So when you bring these things together, that's the first thing you want to think about, which then would tend to lend itself to one of the smaller designs. So you could think about the existing designs that we talked about there. The eVinci reactor and the U battery are both kind of small technologies. At the end of the day, you're going to be designing something that's part of the challenge. So yeah, I see somebody coming in there with the question, which kind of relates to this, in terms of the heat pipes. Yeah, I would argue that something like heat pipes is an elegant way of removing heat that doesn't then rely on external supplies of materials, be it fluids, gases. So heat pipes could be quite useful, which would then lend you towards thinking about the eVinci kind of approach. But there's a bunch of different ways to do this. I talked about 12 different kinds of SMR design. The ones that I talked about 5 different kinds, and I mentioned 12. That is nowhere near the total amount of SMR designs that exist in the world. There are, dozens, maybe 50 to 100, kind of designs that exist. A lot of them are similar. A lot of them share characteristics. But that's part of this challenge, is to work out which technologies you want. Which ones are more suited to your environment, to your need, which ones are safer. So the kind of core that you've got for, say, an eVinci reactor is designed for remote deployment. So it's like in a vessel or in a containment that is, maybe 20 tons or so. So they built something that is doable. Now, can you fly, if you call it flying, can you fly 20 tons of reactor to Mars? Or can you get 20 tons off the surface of the Earth in a load? Maybe one of those heavy lift satellites, one of those heavy lift rockets, perhaps. And then you've got to think about how you bring that and how you take it. Equally, then you want to think about fueling. So fueling is going to be an issue. So which fuel do you want to use? Do you want to use something that needs refueling often? That wouldn't be very elegant, because then you've got a whole bunch of trouble. So you've got to want a unit that is pretty resilient in terms of fuel. So that, when you look at the arc reactor, it talks about a 20-year refueling cycle. Maybe that's the kind of number that you want to look at. Trying to mitigate the need to refuel. That might then constrain which design options you want, whether you want a fast reactor or a thermal reactor, which kind of enrichments you need. All of these things come into play. But I would say that if you were to lean towards different kinds of technology, I have a feeling that for remote deployments, like in space, the ability to not have leakage of any of the fluids that might be necessary for the operation of reactor, I think, would be key. Because even if it didn't cause an accident, if you wanted to use water and the water has different characteristics. Now, one of the things you want to think about is like gravity. How is the gravity in space compared to elsewhere? What will that do if you're talking about condensation? What impacts might that have? So it might be fine on Mars, but it might not be fine on the Moon, for instance, where the Moon has 1/6 of Earth gravity. So when you think about passive safety, you've got to think about all these other kind of aspects as well. Kind of rambling answer, but it's what comes to mind.
I have another question with respect to shielding. I think we haven't touched much about shielding. So what's kind of a consideration that you had to think about it when you're thinking about shielding of a reactor? Like, if you were to use that as the power source for first colony on Mars.
Okay. So first up, if you've got a new reactor with new fresh fuel, well, the need for extensive shielding in initial transit is going to be low, just because it hasn't fissioned yet. Therefore, you don't have any fission products that are going to make the radiation that's going to give rise to a risk to health. That's the first thing. Secondly, you can think about where you're going to locate this in terms of your Martian base. Are you going to have it on top of where your camp is, or a little bit further away? Are you going to dig a hole? Like, again, back to the excavation side of things. So you need to think about what kind of materials that you would require and what you're shielding against. So we think about neutrons. With neutrons, I'm sure Philippo talked about this a couple of weeks back. You typically want light stuff. So you want to think about Water's good, but water might not be good to get to Mars if there's no sufficient water there. Plastics are good, oils are good. Anything hydrogenous is typically pretty good for that kind of thing. If you want to stop gamma rays, you either need a lot of material so that there's enough of an interaction, or you need some heavy stuff like lead or tungsten. And so they all form part of the shielding that you might need. So you see that some of the SMR designs have gotten around this by digging a hole. You could also build up. I'd argue that on the surface of Mars, I don't know if aliens exist, but I would argue that there's much reduced chance of an airplane flying into a reactor. So physical security methods or physical security reasons for putting the reactor in a hole is less key. But we could think about bringing material up or just putting it far enough away and running cables. So there's a range of different approaches, like I said, but I would argue that you'd want to try and use as much of the material on Mars that's there now as possible, because that will reduce the amount of material you need to take with you. And that's the same for all of these things. So anything that you can use on Mars from Mars is advantageous. Is that an SMR when you get into that side of things? The unit itself coming in from Earth, of course.
Good day. I have a question.
Okay.
Yeah, I'm not sure if I missed this earlier on because the connection is kind of shaky over here. But are we choosing between the designs you presented today and then seeing how we're going to deploy it and set it up? Or are we creating our own SMR design? I'm a bit confused.
Okay.
You can create your own SMR design. Yeah. Right now, it's open up to any design.
So what I've shown you is a range of different possibilities and the kind of considerations that have been made in the design of those. And they're principally reasons around safety or control or availability of materials. All of those come into the mix. So when you're thinking about going to somewhere like Mars and taking a reactor with you, those are the kind of considerations you want to think about. So if you looked at NuScale's reactor, obviously requiring a lot of water, that might be less suitable. Equally, it's something like 9 meters tall. So that's then maybe a constraint on the volume of reactor that you could take on your spaceship. Don't know how big the spaceship would be, but you could look at what I forget, is it a Falcon rocket? What kind of load capacity, lift capacity it's got in terms of what it could take. But you also want to think about when you're lifting off from Earth, maybe even, if you're taking nuclear materials up on a rocket, you want to be pretty sure the rocket doesn't crash because it will then deposit everything on Earth. So that might also be something to consider in terms of your design choices. How much material comes in one go. They're within the bounds of whatever your design constraints are. They're all things that would be thought about in reality. Yeah.
Is there any
Thank you.
got it.
Go ahead, Salam.
Thank you, Salam Ali. I got a question. First of all, thank you for the informative lecture. And my question is about the licensing process or licensing status of these different SMRs designs. Do you have any idea what the status of these different SMRs design and how far is from design license or construction license?
I think all this stuff you can look up on the CNSC website. If you look at where it talks about the vendor design reviews, they're all in different stages. Some are quite immature and some are much more mature. Realistically, are we going to be building one within the next few years? Maybe not. Maybe mid-decade we might have get an approval to build something, but none have actually been licensed yet. The only one that has received a license outside of Canada is if you were to look at the US, and there's obviously NuScale has gone through. Now, if you're thinking about Mars, obviously, what is the regulator on Mars? Would you have the same regulator? For your design, for the design challenge, is the CNSC the default organization to go to? I don't know.
Is there any other questions from the audience? Okay, seems like there's no other questions. Okay, there's another question just popped up from Adam.
Yes. The answer is yes.
Okay, thanks everyone for joining our SMR X Hackathon Design Challenge lecture series. I just wanted to let you know about the SMR X Hackathon is going to be on June 6th from 11 a.m. to 3 p.m. using our Mozilla Firefox Virtual Reality Hub. So make sure that you form your teams and get together, talk to your teachers, your mentors, and register online. So the online registration is available through our FESNS website. The information is provided to you before. So also this will actually get us into our next lecture by Dr. Alvaro Cuedo from Faculty of Business. He's going to talk about the virtual reality and augmented reality and how you can use this technology for the design of our small modular reactor. So we will be meeting in a virtual reality environment to the design on the June 6th. So what we're going to have two big domes. One big dome would be to facilitate the event, and then you will have your own virtual reality dome that you can do your design with your team. So you can get together with your team and the mentors and do the design, and using what we call is a shareable drawing board that you can do a design. And then finally at the end, one of your group members can bring your design to the main dome where you can actually present your design to the judges.